Thanks, Todd. Thank you. I'm really delighted to be here. And of course, you know, my connection with large deviations now goes back, a number of years. And what I decided to talk about, I think it might be slightly different, although some of these aspects have been covered throughout these weeks. And it's the application of large deviations, dynamical large deviation, because applying it to dynamical problems. Well, here is quantum non-equilibrium. More specifically, it will be about open quantum systems. This is, in Nottingham, and this is also within the context of this new Center for Quantum Non-Equilibrium we have there between physics and maths. And part of the idea is to try to connect, methods, concepts from classical stat-mech to problems in quantum, physics. So that's what I'll try to do, is try to, transport some of the ideas across the classical quantum divide. So I say this very often, my battle cry is dynamics is more than statics. And this will touch upon some topics we heard about yesterday as well. So the canonical example are classical glasses. In the sense that if you take a chunk of glass and you look into its statics, into its structure, you think it's a liquid that would flow. Of course, it doesn't. So it's really everything in the dynamics. And how materials like glasses, before they actually become glasses, relax is complex. And the complexity, the interesting structure, if you want, is in the trajectories. It's just a projection of a trajectory, how a supercooled liquid relaxes. And I won't go into the details or even show you anything about this, but this is called dynamic heterogeneity. There are space and time correlations that become very pronounced, and you wouldn't see this on the structures. So this is contained in the trajectories. So what one needs is a stat-mech for trajectories. And one can construct this with large deviations. And this, in the context of thinking about glass problems, this is what we've done for a number of years. Of course, with our late and much missed friend David Chandler, also with Rob Hughes here and others, some of the papers. So what I will talk about is how to, construct something similar using large deviations, so a stat-mech for ensembles of trajectories, for problems in quantum systems, in particular open quantum systems. That's quantum systems interacting with an environment. Yeah. And this is a program of work we started with my colleague Igor Lesanovsky in Nottingham, a few years back. So I'll start essentially from this paper and build up. And what I want to do is just explain the basic ideas and give you a few examples and some of the questions we're thinking about, and try to have a discussion with you about this. So, what are open quantum systems? Certainly in the sense that I want to take them. Imagine you have a big quantum system, sketched there, of which there is one part that you're interested in, I'm calling that the system, and the rest is the environment. Yeah? And this big quantum system altogether is isolated, so evolves according to some, unitarily according to some big Hamiltonian, calling H tot, of which one part is the Hamiltonian that applies directly to the system. One part is a Hamiltonian that applies to everything else that I'm calling the environment, and there is a Hamiltonian that provides interaction between the system and the environment. So this unitary evolution, as we know, Schrödinger equation, that's the state of the system and so on. But imagine under certain conditions, we are interested only in the system. We imagine the environment is very large, the interactions are weak. We can reduce the description from that of the whole system to that of the whole system plus environment to only that of the system, because we are tracing out degrees of freedom. In this case, the ones of the environment. The description will have to be in terms of a mixed state rather than a pure wave function, a density matrix. And means a way that we'll see in a second, the effect of the environment becomes effective on the evolution of the system. So now, here comes an approximation. I won't, do it in any detail at all. I just say that the assumptions are that the interaction is weak, that the environment is very large, that its correlation times are very short. Being large, having short correlation times means that any information that goes from the system to the environment doesn't come back. And therefore, one can describe the effective evolution by doing perturbation theory to the second order in terms of a local in time quantum master equation for the state of the system that has this shape. And this often goes by the name of Lindblad. Of course, there are other people, associated to such a quantum master equation, Gorini, Kosakowski, and Sudarshan as well. But this is usually called the Lindblad master equation. So it's an evolution equation for the state of the system, the density matrix. It's a linear, because this is a matrix or an operator if you want. There is a linear superoperator that acts on it, and it has a structure that once you unpick it is familiar to those of you who, at least when I came to this problem a decade ago, come from the classical angle. Because essentially it has the structure you're used to of a master equation for Markovian dynamics, except that it has, of course, the quantum aspect to it. So there is one part, so this was the original Hamiltonian acting on the system, so that's, for the density matrix, that is, the same as the Schrödinger equation, the so-called von Neumann equation. And then you have terms that are the consequence of the interaction with the environment, that under this, perturbation theory end up looking quadratic in what are called jump operators. Look, these terms are positive, there's J and J dagger adapt on it, so these terms are negative. This in principle is imaginary. So those are the terms that produce jumps. The positive terms in a classical master equation are the ones that give you the changes of the state, and the negative terms are the ones that conserve probability and are associated with escape rates. And this is basically what the structure of this equation is telling you. So now what you have is not only the coherent evolution, but the action of the environment. This would have given you unitary dissipative evolution, so you have a combination of dissipative and unitary. Overall, dissipative will win. So this is why this, is a quantum dissipative dynamics. So this is a generic structure, and all that this requires is that these operators are bounded. Okay? And this is coming from the fact that the interaction Hamiltonian, this is an operator on the system times an operator in the environment. So you have an interaction Hamiltonian that looks like this, sum of this is a kind of quadratic in the terms that this is an operator in the environment, in the bath, and this is an operator in the system. This is what the interaction Hamiltonian looks like. You do second order perturbation theory, and what remains, because you've traced out of an environment, is this part on the system. Yeah, and the bath is essentially just a collection of free fields, okay, with a certain, spectral property that ends up giving you this. Just one way to derive it. The other one is, if you want, a la Lindblad, which is saying what's the most general local equation for the state of the system that preserves the physical properties of the density matrix. It has to be of this shape, okay? This is what's sometimes called a completely positive trace-preserving map. What's the most generic local in time equation I can write? It has to be like this. And sure enough, it is of this kind if you do this conservative treatment. And so what you have is, this generates motion, and if you integrate this equation, what you have is the evolution of the state of this later is the application of this exponential of this operator to the initial state. And because this is dissipative, under relatively general conditions, at long times you go to a stationary state. Okay, the dissipation gives you stationary, maybe more stationary than one stationary state if there is no reducibility, if there is no irreducibility, but in general you go to a stationary state. Like, sure. I'm just saying that, as we see in a second, if you give me 2 slides more, this part and this part are associated to the escape rate of the corresponding quantum Markov process that this equation is describing. Okay? So I'm going to try to emphasize the analogies, and then I'll go to examples. Okay. So that's the master equation. It preserves the properties of the density matrix, hermiticity, preserves the trace, and the positivity. So now this is just I was just trying to say, let's do the conversion table. yeah, between classical and quantum. Imagine you have a classical master equation, writing it in this operator form. It's a probability vector and a master, you know, and a master operator, could be a Fokker-Planck operator if it's continuous and so on. So that's the quantum master equation. Again, a state is now described by the density matrix, and this super operator is the generator. Probability is conserved. If you sum from the left, use stochastic generator, which is multiplying by this flat vector on the left, you get 0. That means that the adjoint, in the quantum case, is that the action of the adjoint on the identity is 0. That's probability conservation, is easy to prove. There is a stationary state vector in this, you know, classical case. There is a stationary state matrix in the quantum case. And you know, this is a description of this of the probability, but associated to, you know, just like always in stochastics, associated to this generator, there is a, you know, there is a dynamics in terms of stochastic trajectories, in this case, jumps or evolution of configurations. There is one that we'll see in a second, associated with the quantum case. So the master operator generates, or in the jargon can be unraveled into a quantum Markov process, which is corresponds to run, you know, to stochastic trajectories between pure state, between wave functions, and we'll see that what it is in a second. I'm just trying to emphasize this, you know, direct analogy, and furthermore, the analogy is not, you know, just a coincidence. This description contains that description. If there is no Hamiltonian and the jump operators have certain properties, then all the evolution occurs on the diagonal of the density matrix. The diagonal of the density matrix is a probability vector, so you can embed these dynamics in there. Which, by the way, it's interesting because that's a way to construct, you know, dissipative problems, classical dissipative problems, to which you can then add coherent effects in a way that's different from what's, you know, it's often been done, and try to understand, you know, the moving away from the classical classical stochastic limit. So now, so when I say classical trajectories, I think of something like this, you know, in the case of a continuous time Markov process, and that's what, you know, an operator like this, you know, will be associated with, is you're in some configuration, you stay there for a period of time, that period of time is distributed according to the escape rate of that configuration, then you make a jump, then you, you know, wait for another time, you make another jump, and so on and so forth. And trajectories look like this, jump between configurations. And the probability of state of the, you know, the probability vector at any one time is, you know, making a cut there at that time and adding over all possible configurations. So averaging over all possible trajectories, averaging over all trajectories gives you, you know, the deterministic evolution of the state of the system. Exactly. Mutatis mutandis, this is what occurs in the quantum case. So one can unravel the dynamics, these deterministic dynamics for the density matrix. The density matrix is like a probability over wave functions. So the associated Markov process is a Markov process that occurs, a quantum Markov process that occurs on wave functions. And it has this shape. So you start from some, you know, specific state, you quote unquote wait, but because this is a quantum problem, you don't quite wait. You evolve with an operator that's constructed from the Hamiltonian, and the operator that was on the negative part of the density matrix associated with the jumps. And the evolution, I haven't written it here, is the exponential of minus it, this effective Hamiltonian. So it would be unitary without dissipation, but it's non-unitary because this operator in general is non-Hermitian. So that evolves the state, but also gives you the time at which you make a jump. And the jump is an application of one of these jump operators to the state of the system. Then you evolve again, you jump, you evolve again, you jump. We'll see an example in 1 second. But this is basically the same as before, except it's quantum. It's a quantum Markov process. A jump between wave functions in this case. And sure enough, if you take one time and you average over all of these quantum trajectories, you get back the deterministic evolution of the density matrix. Psi is any wave function. So it's a wave function in the state of the system. It's a vector, so it's a pure state. It's not a density matrix, which is a mixed state. And you know that wave function evolves rather than evolving unitarily as it would with the Hamiltonian only. It evolves in this kind of finely unitary dissipative way there, and then it has sudden jumps, sudden changes. I have an example, a couple of examples coming up. Well, in a Markov case, this would be a configuration So you would don't, okay, so if you can think of a vector space, same problem with the same, set of classical configurations. In a Markov problem, the trajectory is jumping between configurations, which in a, in Hilbert space, if you want, would be jumping between, the unit directions of your Hilbert space. But in a quantum problem, the vector could be anywhere. That's the distinction. That's the quantum part. So once again, in the case I showed before, here you're jumping between one configuration, another configuration, another configuration. Imagine you have 3 configurations. Yeah? So you have a Hilbert space which is 3-dimensional. The probability can live there, but a classical trajectory is configuration to configuration to configuration to configuration to configuration. In the quantum case, you can construct a wave function in that same Hilbert space, but you evolve, the wave function could be any superposition. The way you calculate average is different. In the classical case, you just calculate averages with the probability. In the quantum case, expectation values are bilinear in the vector and so on. Is it clear? Exactly. In the classical case, this operator is diagonal. That's why in the classical case, between jumps, you don't change the state. All that this operator does to you is give you a number, how long you have to wait, or how the times are distributed. In the quantum case, this operator is non-diagonal, so it gives you both the evolution of the state between jumps, and we can discuss what the physical meaning of that is, and it gives you how the times are distributed according to this formula here. Okay? Let's come to an example and see. Yeah, you take note of the questions. Yeah, never mind. So, so this is how the state of the system evolves. Of course, in quantum mechanics, you cannot just look at the wave function. We can look at configurations classically and nothing happens because we don't necessarily disturb them. But quantum mechanically, you cannot look at the wave function. So this would be what's either happening and you don't see it, or what's happening in your computer if you're simulating it. So what does one, quote-unquote, see? So what one sees is that every time there is a jump, this is a direct effect on the environment. Remember from this interaction we had originally. Yeah? So every time there is a jump, there will be a signal in the environment, and this generates, if this is the quantum trajectory, the signal in the environment generates a quantum jump trajectory. For example, typical situation in quantum optics, you have some atom or collection of atoms, and you're addressing some levels with a laser, and the system is doing its thing, and every now and then, the interaction with the environment is manifested in emissions of photons. So you're outside, you're not looking directly at the system, you're looking at what's emitted from the system. Because you're looking at something that's emitted from the system, you get information that's associated with these jumps, and the information you get is, clicks in your photon detector. Yeah? So from the classical information you see outside in the environment, you glean something about the actual behavior of the system, and that's what's called a quantum jump trajectory, because associated with each one of these detected photons, let's use that language, or detected events in the environment, there is a quantum jump of the actual state of the system. And people do this. We'll see an example. Okay? So this is a quantum trajectory, and this is a quantum jump trajectory. This is the observed time record of quantum jumps. Let's look at the problem. Model 1 of an quantum optics textbook. Okay, so it's a good place to start, and it will happen to be not completely trivial. Imagine could be an atom, and you're addressing 2 particular atomic levels, and you're shining a laser that's on resonance, and it's being described in the rotating frame of this problem. So at the end, the Hamiltonian for a process like that is one where there is a driving with strength omega, and there are 2 levels. It's like a quantum, quantum spin a half or a qubit, and the operator in the Hamiltonian is sigma x, which is the operator that flops from take this state to that and takes this state to that. So that's the straight line I'm drawing there. So it would be the quantum drive on the 2 lines. And the interaction with our environment goes by many names, but imagine it's what's called zero temperature, which means that the environment wants to remove energy from the atom, in this case represented by the environment likes to collapse the state 1 to the state 0. This is this wiggly line. So this is a coherent process, and this is the interaction with the environment. It's a dissipative process. It's described by a jump operator with a certain rate and the operator is sigma minus, which takes 1 and puts it into 0. Okay? So this is the dynamics. You are driving it coherently, going up and down, and every now the environment pushes it incoherently down to 0. So that's the Hamiltonian, that's the jump operator, that's the master equation. Those are the operators written in this basis 0 and 1. Okay? So Hilbert space is 2-dimensional, the matrix is 2 by 2. So as an operator problem, this master equation is you have an object of 4 entries, the density matrix, the operator that acts on it is a matrix, quote unquote, of 4 by 4. Okay? So it's a problem that at least Mathematica can solve for you if you want. So sure enough, so if you look, and I'm choosing certain combination of gamma and omega where square roots go away and the numbers are simple. For example, in the stationary state at long times, you go to this particular density matrix. These are the probabilities of being up and down. So 1/6 of being up, 5/6 of being down in the stationary state, and some coherence. This is not diagonal. There is some quantum coherence between the state 0 and 1. So that's solving this. So what's the trajectory? This is solving the density matrix. What are the trajectories? Like I said, it's jumping up and down. Evolving, jumping, the structure I showed you before. In this particular case, imagine you start from 0, you evolve with the effective Hamiltonian that you construct out of this and the sum of j dagger j, as I showed you before, but it's not quite written here. But again, it's a matrix. And then you jump, which is applying one of these. The jump brings you back to 0. So what you have is 0, evolve, some random time, pull back to 0. 0, evolve, random time, pull back to 0. So in this simple case, in terms of the jumps, this is a renewal process. Okay? But this is not a Poissonian renewal process as you would have in a simple classical problem. And it's not just a Poissonian renewal process because the way that you build up the state 1 before you go down is through this effective Hamiltonian. So in a Poisson process, the survival time, the time you spend between renewals is exponential with some rate e minus gamma t. Yeah. But here, if you calculate this, here's the effective Hamiltonian. It's a matrix. The survival is the times between jumps is distributed according to this survival function, 0, the exponential of that effective Hamiltonian, the dagger of that operator, 0 again. And if you calculate it, it's an exponential with some polynomial terms down here. And if you expand this, while the exponential expands linearly, this expands quadratically. Okay? And the meaning of that, and this is known, you need some build-up time. In a classical renewal process at Poissonian, you can renew at any time. But in a quantum case, because populating the up state comes from the Hamiltonian, you cannot renew immediately. And that's contained in the shape of this function. Sorry? Well, because I chose gamma equal 4 omega, sorry. The function of here it will be slightly more complicated in that case. Okay? So I chose this to remove all square roots from solutions of the equations. Okay. So now where comes no large deviations up till now. So now these are dynamics, and I want to do large deviations. I want to start classifying these trajectories according to some dynamical observable. For example, the number of jumps, of quantum jumps, up to time t, because I'm saying that this is a kind of observable that I would actually see in the environment. So, and large deviation principles apply, so if time is large, this is exponential in time times a rate function, which is a function of the observable, which is extensive in time divided by time. One can calculate instead the moment generating function. It's also exponential in time at long times times a cumulative generating function, or just a large deviation function if you want. And these are related by Legendre transforms. So this behaves like a free energy, that behaves like an entropy density. And this is the same construct that we would do in classical StatMech. We already have our, a dynamical StatMech, in this case of quantum trajectories. As usual, this cumulative generating function can be obtained from a tilted operator, in this case a tilted superoperator that can be constructed from the original generator, as usual. And for this particular case, because we are just counting events, is a tilting of the part of the operator that makes the jump. We take this operator, the original one, we multiply e by minus s, this guy becomes the largest eigenvalue of this operator. And the StatMech analogy continues because this is like a partition sum, and we calculate the partition sum via transfer matrix, and we reduce the free energy from getting it from the partition sum to getting the free energy from the largest eigenvalue of the transfer matrix, as we do in standard StatMech. Oops. So this can be done. You plug it in Mathematica. You say, please diagonalize this 4x4 matrix, and that's the answer. Yeah, and I'll just show the results, and we'll discuss it. So that's the problem. In black, we have the function. This S is the field that's conjugate in the moment generating function to counting number of jumps. So that function has this particular shape. You can Legendre transform back into the rate function. For comparison, there is the Poisson. Yeah? And already I think I said that this is non-Poissonian. You can see at the level of the rate function. So that's first interesting result. So the rate function is narrower than Poissonian. That means that the fluctuations in the count are less pronounced than sub-Poissonian. They are sub-Poissonian, and that's also known as anti-bunching, because between events you have to wait a little bit. The waiting a little bit gives you anti-bunching. It's very interesting because this is a rate function. If the 3 wasn't there, this would be the rate function for a Poissonian. The 3 changes it, and it's a rate function what's called a Conway-Maxwell-Poisson. That's not a completely known, at least in physics, because it is coming from computer science or something, class of distributions which are generalizations of the Poisson distribution, where the numbers that you put here in the rate function control whether they are narrower or wider than Poisson. So it's an interesting, simple class of problems that, accounts for sub or super Poissonian statistics. Conway-Maxwell-Poisson. Okay? And no, it's not Maxwell. It's another Maxwell, a computer scientist. Okay? So the derivative of the rate function, the first, the Kieman generating function is the average number of emissions if we tilt. That's the typical number. The trajectories look like this. For positive S, we have smaller number. The trajectories have fewer clicks if you sample them. Here you have a higher number, it's the inactive side, as we would say, the more active side. You have more clicks. So this is how it looks. Another interesting result, which wasn't necessarily known before doing this procedure, even the simplicity of this problem, is that if you take the variance as a function of S, the second derivative of this quantity, and you plot it in the way that in quantum optics they plot the things like what they call Mandel Q parameter, which is comparing fluctuations to Poissonian. Well, that's the value you get for typical behavior associated to this. But look, it's flat. So, the average number of emissions depends on whether you tilt or not, but the fluctuations do not. It's measured compared to the average rate, as compared to the, by this Mandel parameter. And that's an interesting result. Q, sorry. You want me Q? You want Q? Q is variance of the number of emissions over the average minus 1. So it's a quantity that's standard in quantum optics. So if it's Poissonian, this guy is 0. If it's sub-Poissonian, it's negative, and if it's super-Poissonian, it's positive. Here it's negative because it's sub-Poissonian. That's what you expect there. What's surprising is that it's flat. So if you concentrate on subsets of trajectories which are less active than typical, or subset trajectories which are more active than typical, of course they have more or less emissions, but if you plot them like this to quantify the fluctuations don't change. That means that in this particular problem, there is some kind of scale invariance. If you scale away the average, the way that this fluctuates when it's more or less than typical is the same. And sure enough, one can prove that there is scale invariance here. I don't see how you can see this here immediately, just by diagonalizing this guy in 4x4 in any other way. So this is one of the simple uses of this procedure. Yeah. Oh, yeah. This is also true for a pure Poisson process. So this is related to this, generalized Poisson property. When a pure Poisson process, you're not, this is slightly technical, but you're not surprised because the tilting is just changing the rate. So if you rescale by the rate, you don't see the change of the tilt. But it also occurs here. This wasn't necessarily known, okay? And this is what they're saying. This is because you're unfolding, you're unfolding this way of looking at trajectory space using tools that were more associated to thermodynamics or stat mech, and it gives you access to this behavior about fluctuations. So a more complicated problem. We saw yesterday, in Freddy's talk about intermittency. Imagine you have 3 levels. This is again textbook problem. This is associated with blinking quantum dots and things of that kind. Suppose you have now the 2 levels and a 3rd level, and such that every now and then you can park yourself in a level that does not emit, because that rate is very small. So this is an experimental picture. So what you see is a lot of emissions, no emissions, a lot of emissions, no emissions, and so on. Yeah. So again, you can write the Hamiltonian. There is a single jump operator, another operator. This super operator is 9 by 9. Mathematica can still do it for you. This is how it looks. The gray was the old result. Now you have this black scale cumulant generating function. It has much more structure. It changes a lot from the left, more active, to the right, less active. The emissions, that's a typical number of emissions, but there is a considerable change from the left, lot of emissions, to the right, very few emissions. At that value, you have trajectories of this kind. There is a large susceptibility associated with this change in this order parameter. And this is a crossover. It's a finite system. But if this became sharper, we would associate that with a first-order transition. But this is a crossover of the first-order kind. It's a smooth first-order transition, and all the physics make sense. The free energy changes quite abruptly. The order parameter has smoothed out change. There is a large susceptibility, and there are 2 phases, one which is active, lots of emissions, one which is inactive. Typical dynamics under these conditions is living close to quote-unquote coexistence. And that's what one sees. One sees one phase, a sharp interface, another phase, a sharp interface. So once again, this is just thinking of very simple problem and the dynamics using thermodynamic ideas. One can make it more complicated. I won't go into the details. There's no space here, but one can go many-body, take a transverse field Ising model, make every spin dissipate, so it's a dissipative transverse field Ising model. Now the trajectories look intermittent both in space and in time. In this problem, there can be a phase transition in the stationary state. One can study the dynamics, and there is a coupling between stationary state and dynamics and so on. And we've written lots of papers related to metastability, super interesting. And by the way, these are problems people look at in the experiment. They have to do with Rydberg atoms and so on. Okay. I have, my clock says 8:30. That one says 7:20, I don't know why. So let me say, I want to mention 2 problems. I probably won't have time to go into a lot of detail. The first one is the problem of prediction and retrodiction. So I probably show the problem, show what we think is the answer using large deviations, and then say one more thing at the end. So this is the problem. This is actually a problem of interest. Imagine you have a quantum system and you're observing it, but this also applies to classical problems. It could be a hidden Markov dynamics, where you don't know everything about the system. Now imagine you start, for simplicity, in the stationary state. The system evolves, and you're observing the trajectories, and you have some information about that trajectory. Then at some intermediate time, someone, Hugo, let's say, makes a measurement. Could be a perturbation in the classical case, but doesn't tell me what it is. Then the system keeps evolving, and I keep observing, and then at time ends there. And then I'm observing the trajectories, and he has done something in the middle without telling me, and I have to see whether I can infer or get better information about a guess about what happened there from observing the trajectory before the evolution, and more interestingly, from observing the trajectory after the evolution. Okay? And the idea is the following. In the classical case, yeah, it could be a perturbation, and I'm not necessarily observing every detail, because then I would understand the change in the configuration. In the quantum case, if there is a measurement, even if I know everything, if someone measures, they do something drastic to the wave function, yeah? And if I don't see that, I don't understand what the change was. Okay? My observation is only partial. Okay? So, using the past information, sometimes called predictions, if I know how this has evolved, I have a better idea what will happen there. Because if I know nothing, I started from the stationary state, these are stationary trajectories. I know nothing, my guess there is that this is distributed according to the stationary distribution. But if I saw particular properties of the trajectory, I know, oh, hang on a minute. the trajectory did something, so it's more likely the system is in these states than that state. That allows me to predict. The interesting thing is this retrodiction part. If I look at what happened afterwards, from looking at subsequent evolution, I know something about what happened at intermediate times that maybe perturbed the system in a certain way such that the subsequent dynamics was different, say, than the typical. So can I use information to get better information about the past? Let me see if I can say this in 3 minutes, then I got 1 minute to say something else, and then I'll stop. So let's say that this measurement has two possible outcomes, plus and minus. So the probability of the outcomes is the same as the expectation value for simplicity. Just two outcomes, the probability of being up or down is just the same as the average. It's being given by the associated directly to the average. So now, imagine I know nothing, and I started from the stationary state, and I don't use any information. So my guess for the average is that, I sum over all possible trajectories. So it started from the stationary state, so I assume that there I was at the stationary state, and I'm writing it in a vectorial form that applies formally both to classical or quantum. Then I make the perturbation, make the measurement, that's this operator in the middle, and then I take the trace. I sum over everything, which is the same as saying I don't consider any information into the future. That's the most, elementary estimate I can make of this. So that's the first way to estimate, that the probability is given by assuming that I'm in the stationary state, I sum over all possible trajectories here, I sum over all possible trajectories afterwards, and that's my estimate. Then I can use information about the past, and sorry I'm kind of rushing, but I want to get to the idea. If I use information about the past, I know that the state I got at this point is conditioned on what I observed. So it's a subset of the trajectory because I have a certain information. So the state will not necessarily be the stationary state. It's a state given that I've evolved and observed something I'm calling K1. Let's imagine a number of emissions, or more detail if you want. And then I say nothing about the future. So this is my conditioning or my estimate according to past information. I call this P of past. If I do the future, and I will skip the details, but it's, for you guys will probably make a lot of sense. Instead of summing over all configurations for the subsequent dynamics, there is another operator. There is a different state, in the classical case a vector, in the quantum case a matrix, that comes from the left that encodes the informations I saw after. I call this EK2 because of the notation other people use. And what we expect is this. So, if the outcome was the probability I predict if I consider nothing is less than the probability I consider the past, and is less than the probability I consider the past and the future. And so it's we can discuss this in the discussion session, but if I use more information about the dynamics, I get a better estimate. In fact, if I use information about after the measurement, I get a better estimate. And this is how you construct, this is states associated with conditioned ensembles of trajectories. Say the stationary state would be conditioning on all, not conditioning on anything, but if you see something that's a conditioned ensemble associated to that conditioned ensemble, there is a final state, or there is an initial state if you're coming from the future. So these are these two states I'm sandwiching here. What's the problem? The conditioned state is hard to calculate. Conditioned ensembles of trajectories cannot be generated easily. It's easier to tilt. But what do we know? Okay, so this is just a picture. The conditioned ensemble is like a microcanonical distribution. It's a value of a certain observation. It's easier to tilt, which is not conditioned on the precise value, quote unquote, conditioned on the average value, like canonical and microcanonical. From various works, including Hugo's, we know that there is an ensemble equivalence at large times. There is also a quantum version of that. So instead of using the conditioned states, which are hard to calculate, one can replace by these tilted states that are much easier to calculate. So that formula can be written using these standard techniques of large deviations. So we can discuss this later, but this is a connection to large deviations of this prediction retrodiction principle. It applies quantum mechanically, but it's a classical version of it. Then there are questions. What's the optimal time to extract information from the future. There are questions associated with quote-unquote entanglement between the past, correlations between the future dynamics and the past dynamics. And this relates to matrix product states. So let me just put one slide, and I finish. I still have 56 seconds, according to my audit of the time. So there's a very interesting formal connection. It may be useful or not. For some of these quantum open dynamics is the tool, it gives you the tools you need to prove things. It might be useful classical or not. I wanted just to flash it. Between ensembles of trajectories, that's collection of trajectories of the dynamics under probabilities, and matrix product states. Matrix product states are typically how you construct wave functions, or if you want probabilities of one-dimensional problems. So you can think of one dimension as being time, and the transverse dimension, which is the dimension of the matrices, as being the dimension of space. And you can encode all the trajectories of a stochastic problem in a big vector whose one-dimensional geometry is that of time. We can discuss the construct. It's related to escape rates and jumps and so on. Classical or quantum, you can do this. So what I'm saying here is that all the trajectories of the dynamics are a big vector that lives in a very big, maybe abstract Hilbert space. Yeah? And when we talk about conditioning and tilting and et cetera, that we do with large deviations, one can formulate as manipulating this vector. Yeah? So for example, when we tilt, which is defining, sometimes we call it the S ensemble, is the set of trajectories where we've tilted the probabilities. In this language, the tilt is going to another vector. Yeah? So we have the original vector, big vector in this arbitrary, abstract Hilbert space that describes all the dynamics. Tilting it is going to another vector. So something that hasn't been discussed, maybe it's been discussed in these weeks, but not yesterday at least, is what's called the dot transform. The tilt is a non-stochastic dynamics, doesn't conserve probability and so on. This vector can be normalized, and there is a transformation that takes it to a different problem that has a real dynamics, sometimes called generalized dot transform. Rob worked on this, and Hugo, and so on. In this language, the generalized dot transform is a gauge transformation. It's taking this vector and making a transformation that changes the vector in the way you represent it, but doesn't change it physically. So it's like rotating in this direction. So the dot transform writes the vector in a way that doesn't change the actual vector, just write it differently, and writing it differently, you have the associated physical dynamics that realizes the tilted ensemble. One thing that's missing, I'm thinking about, and I think it's interesting, in the classical case we have very nice variational ideas for the rate functions, what's called level 2.5 dynamics, that's kind of tailor-made for Markov, continuous time Markov chains. There's no equivalent of quantum open level 2.5 dynamics. And with this, I stop. That's what I told you. Those are people whose work I mentioned. Thanks.
For the prediction problem, when you had the results, this one, when you're replaced by the tilting, so do you have in mind that you have a long time limit behind the estimation problem? Like, are we expecting the real conditioning problem to be
yes.
the tilting problem? Because we're not looking at the equivalence of integrated observable.
That's good. Yeah, that's a good point. This simplest, there's a more sophisticated way to try to make this connection that accounts for, shorter times. But the idea here is that you have some aggregate information of trajectories, and you're trying to connect them at relatively long enough times so that you can apply the equivalence. As I said afterwards, there is an issue how long you want to be. If the time is too long, you have aggregate information about the trajectory, and the time becomes extremely long, that information is not necessarily useful. So in practice, you want a compromise between long enough time so that the approximation is good, and short enough time so that the time gives you something useful. Here I'm using a single observable. This could be a vector, a collection of observables. That's kind of the thing you would like to see. You would like to have the aggregate of many observations of the trajectories. Yeah.
So for the gauge transform at the end, so when you make the Doob transform, you have to mess with the initial and final conditions somewhat. So I'm just wondering, in this geometrical picture, what do I imagine for the boundary conditions in time?
Oh, this is so formal that all it's included, okay? But if you look at this picture, so you're constructing, so the matrix product state is because you have a vector that lives in, this space where the dimension is essentially time, the times where the events take place, and the amplitude or the probability, depending on classical or quantum, is constructed as a product of matrices. There is an initial state, there is a sequence of things, and then it ends at the end. The gauge transform is a transformation that indeed has time. So when I talk here about the gauge transform, is the arbitrary time dot transform that's not necessarily uniform in time. So this is like the Chetrit to Chet full thing. So it applies at this does not have long time in it. At long times is the usual story that there is something at the edges and the transform in the middle is uniform in time. But this is arbitrary in time, has a time, inside this vector there is time in this construct of the matrix product. Okay. No, this holds, we can discuss it. So this is, in this language it's very easy to prove, holds for arbitrary time. So it's a full, you have to solve an equation and that equation has some time dependence and at long times the solution becomes stationary. Yeah.
I also have a question about this.
I use the word gauge transformation because that's the terminology in matrix product states. But people know that matrix product states are invariant physically, under certain transformations, and they're called gauge because this is what Rob was asking. The transformation is something that can depend on this direction. Yeah, so in principle, the transformation depends on time. So I'm roundaboutly answering your question. So generically, the dot transform depends on time. So there is some change you make at the beginning, and then it becomes stationary, and then there is some change that you make at the end. The same occurs here. So it's a transformation of this vector that's time dependent. So truly is that the set of trajectories generated by tilting is the same as a set of trajectories from a non-stationary process. I think that's Chetrit and Touchet's work. Prove that, clearly. The same occurs here, and the language gauge is because it depends on time. Okay? It preserves the set of trajectories. The operator is changing, so of course, it's like in his case, the spectrum of the operator will be changing, and then becomes a stationary operator that changes again.
I guess what's confusing me is it doesn't seem like there's a parameter that you can change that leaves the system invariant.
So I can't hear you, sorry.
It doesn't seem like there's a parameter that you can change that's going to leave the system invariant.
For gauge you mean? Oh, no. Okay, that's a good point. So the gauge, there is a whole class of transformations you can make. I mean, you can make this, if you want, this rotation by as many as an arbitrary angle in this simplified picture. There is one particular angle that brings it to a stochastic form. So that's why it's gauge. That's the answer. So there is a class of transformations that leave this vector invariant. There is one particular gauge. You fixing the gauge in this language gives you the stochastic problem. So you have all this arbitrariness, and there is one where the operator is stochastic, and that's fixing the gauge. Okay, yeah.
Well, I have a naive question about this tilting. In this quantum problem, can you understand this tilting as maybe something physical, or is it just a mathematical tool, the tilting?
So, okay, so this is a question you can ask of the classical case as well. So when you and this relates to what we've just been discussing. So tilting is a way to extract information about the statistics of the original problem. It's appealing because this looks like a different generator, but it's not stochastic. So is this related to another physical problem? The answer generically is yes. This is this dot transform. There is another problem, which is a proper stochastic problem, which has the statistics of this associated to this operator, this is describing rare events of the original problem, if you want. There is another, physical problem whose typical behavior is the rare behavior described by this. You showed, two distributions essentially describing that. In a simple problem like this one, like Poissonian, Grant mentioned this, or other problems, the dot transform is just a change of rates. And in this class of problems, you can go to the rare behavior described by the tilt just by changing the rates of a system of this kind. That's doing the dot transform. The dot transform gives you a dynamics that happens on the same state space, but with a different set of transitions, and if it's any-body problem, it would have fun interactions and what have you. So that's the connection. It's the same problem as classical. Have I answered? So the dot transform, and we've written the general, the quantum dot transform for this, connects this to another generator that's proper stochastic and describes its typical dynamics, describes the same rare dynamics encoded here.
Okay, one last question, then I think we need to keep moving.
So, you have not used the quantum Jaroczynski equation or
Sorry?
quantum fluctuation theorem or quantum Jaroczynski equation because you are interested in the quantum thermodynamics analogy to apply the idea to analyze the quantum master equation. But somebody applied quantum Jaroczynski equation to analyze the quantum master equation. So,
is that the question? So there is a very nice paper by Chetrit and someone else whose name escapes me now, where they've taken this, Lindbladian dynamics and looked generically at fluctuation theorems. And sorry? Malik and, thank you, Malik and Chetrit. Really, really, beautiful paper, where, at least to me, where they look generically at fluctuation theorems with these dynamics. Fluctuation theorems are just statements about conservation of probability at the end. And formally, you have all sorts of fluctuation relations depending on what you observe, on what you're interested in, the quantity. What you don't get is observables. That's the problem in the quantum case, is that these distribution, these relations are not necessarily between observables. There is one specific case, if you have a closed problem and you do two-point measurement and you call that work, then you say, well, that's something I can observe. But there is no observable operator associated with the quantities for which you do the fluctuation theorem. But that also emphasizes that this technology is just a generalization of what we're used to. So if you generalize the ideas that give rise to, in general, fluctuation theorems with this, you get them.
Okay, I think we are going to move on to the next speaker. Thank you, Juan P.
Thanks.